Hello, I am Zhiyuan. Today we'll introduce how fine-grained re-execution improves the performance of distributed transactions. This is a joint work of Shanghai Jiao Tong University and New York University. Distributed transactions are important but also expensive. They suffer from the communication cost of remote data accesses and synchronization. Let's consider an example OCC system. It has database nodes acting as transaction coordinator. It has highly available storage nodes using primary backup replication. For transaction execution, the database nodes need to read data at remote storage. After execution finishes, database nodes send distributed commit messages to the storage nodes for validation, and then one more round trip is used for replication. Please note that even if we collocate the database nodes with storage, multi-partition transactions and the replication still introduce the communication cost. For reducing communication cost, caching and batching are proven techniques in distributed systems. In the case of distributed transactions, caching can decrease the need for remote reads, while batching can help amortize the cost of remote synchronization. This leads to an intuitive question. Can we use classical techniques like caching and batching to boost the performance of distributed transactions? Then let's give it a try. First, we extended the previous OCC system with database-side cache. Here is an example. Transaction T1 executes locally with cached tuples and tries to commit after execution. At the same time, T2 starts execution before T1 commits and updates the local cache. While caching reduces the number of remote data accesses, caching alone is not enough. The current system has the problem of limited parallelism due to remote synchronization. In the example, T2 will be aborted eventually, as it cannot observe T1's write until T1 commits. To amortize the cost of validation and replication, we leverage batching. The difference is that after T1 finishes execution, it directly updates the cache. Thus, T2 can observe T1's write without waiting for T1's commit. After T2 finishes execution, T1 and T2 are merged into the batch with deduplication and committed as a single unit. Now, with batching, T1 and T2 can both commit. The previous example seems enough to illustrate the feasibility to optimize distributed transaction with caching and batching. However, upon examining the design of existing systems, we found that they do not fully exploit caching and batching. Although Amazon Aurora and Alibaba PaulaDB apply both techniques, they are restricted to a single writer design, which means they do not support multiple database nodes writing to the same tuples, thereby limiting performance. Apple Foundation DB, Cocoa, and Sundial adopted a multi-writer design, but do not utilize caching and batching simultaneously. To dig the reason, we conducted an experiment using TPCC new order transactions and incrementally introduced caching and batching into the OCC system. When all transactions were limited to a single partition, the peak throughput increased by a factor of 16.7. However, when roughly 10% of the transactions involve multi-partitions, the performance drops significantly. This leads us to conclude that conflicts between transactions have a large effect on performance. When database nodes access common tuples, their caches are more likely to be stale and increase the abort possibility. On the left is an example transaction execution in the form of dependency graph. In the example, T1's read access steals cache, and thus T1 is aborted. As batching merges transaction T1 and T2 as a single commit unit, T2 in batch 1 is also aborted even if T2's operations are valid. Finally, as batching allows transactions to observe others on uncommitted writes, it has the risk of cascading abort. With the three factors, transaction conflicts are amplified and make abort expensive. This leads to a new question. Can we handle conflicts in a cheaper way? The answer is yes with our key observation. A large portion of operations are unnecessarily aborted. In the previous example, only 3 operations are really affected, where caching and batching cause all of them to abort. The observation leads us to think of re-execution invalid reads and operations affected by them. This comes the key technique, fine-grained re-execution or transaction repair. We propose HighCrunch, a distributed transaction system that can fully utilize caching and batching through fine-grained re-execution. In the following talk, we will introduce its architecture and transaction execution, its distributed commit protocol, and one optimization that avoids two-phase commit overhead for a specific type of transactions. HighCrunch consists of a timestamp server, a set of database nodes, and replicated storage. Clients directly send transaction requests to the database nodes. The database nodes first execute each transaction individually. At the same time, it also tracks the operations dependency for re-execution. After enough transactions finishes execution, they are merged into one batch with a total order. Finally, the batch starts the batched distributed commit. To enable fine-grained re-execution, HighCrunch needs to track operation dependency. It classifies dependencies into 2 types. The first type is intra-transaction dependency. It provides developers with data flow-based programming abstraction for writing stored procedures and converts the stored procedures into static dependency graphs. For re-execution, HighCrunch guarantees that transaction execution is deterministic. The second type is the inter-transaction dependency, which is generated at runtime. HighCrunch simply records the accessed tuple's key and version. By detecting the changes of key and version, HighCrunch knows whether a read operation needs repair. Then we introduce HighCrunch's batched distributed commit, which uses a two-phase commit-like protocol. Compared to two-phase commit, it has 2 variations. First, HighCrunch relies on a centralized timestamp server to align commit order. Second, HighCrunch repairs transactions during the prepare phase. HighCrunch relies on the timestamp server to construct the commit order between transactions. With the commit order, replicas of different storage nodes handle conflicting batches in a consistent order. This enables HighCrunch to use a quorum-based replication protocol. It unifies validation and replication in one network round trip. With the consistent commit order, HighCrunch also ensures that when a batching is being repaired, conflicting batching cannot be committed, ensuring each batch is repaired at most once. To enhance parallelism, the commit order is a partial order instead of a total one. After the commit order is determined, the database nodes start two-phase commit, prepare, and commit phases. With quorum-based replication, the database node broadcasts prepare messages to all target storage nodes replicas, unifying validation and replication in one round trip. The storage nodes then assign tuple-level read-write logs according to the commit order. After batch's logs are all acquired, storage nodes do validation and logging and send back the results. If validation succeeds, then database nodes broadcast commit messages. The storage nodes in turn apply the writes and release the logs. In case where validation fails, the database node needs to repair. Storage nodes include the fresh tuples in their responses, ensuring repair is based on up-to-date tuples. After repair, the delta of write set is piggybacked in the commit messages, ensuring the storage nodes are aware of the changes. To repair a batch, the database nodes sequentially executes transactions within the current batch, following the total order in which they were merged. Let's consider an example where T1 reads a stale version of tuple B, resulting in failed validation. The storage node sends back the up-to-date version T6 and triggers the repair process. The database node then executes the affected read and write operation of T1, generating a new version of tuple B. To differentiate the new version from the original version written by T1, HighCrunch marks the tuples as repaired. Then a similar re-execution process is performed for T2. With the help of deterministic execution and a consistent commit order, a transaction's repair is successful in most cases, except for two specific scenarios. First, when its read-write set changes. Second, when it triggers user-initiated aborts. In both the scenarios, the corresponding transaction is aborted individually without causing other transactions in the batch to abort. So far, we have known how HackerRanch executes, repairs, and commits transactions. Let's take a step further and introduce a fast-pass commit optimization designed for a specific type of transactions known as one-shot transactions. Please note that transactions in well-known TPCC benchmark are also one-shot. In our setting, a one-shot transaction's dependency graph can be statically decomposed into multiple subgraphs. Each subgraph accesses data within a single storage node and reaches the same commit decision independently. Therefore, different parts of one-shot transaction can be repaired independently on each storage node. If a batch consists of all one-shot transactions, then the batch can be committed in the fast pass without two-phase commit overhead. Specifically, the storage nodes can repair transactions on their own. Thus, they can release lock directly after replying to the database nodes, reducing the storage side lock duration from one round trip to 0. This enables the storage nodes to pipeline commit process without interrupted by network messages. Due to time limitation, please refer to our paper for more details. Then, we first give the breakdown results on TPCC benchmark compared to baseline's OCC system. HackerRanch's peak throughput is 16.4 and 13.7 times higher for different percentages of multi-partitioning order transaction. Further, HackerRanch's throughput is times higher than FoundationDB and Coco on TPCC benchmark. Finally, we reached a conclusion. We present HackerRanch, a high-performance distributed transaction system. It executes distributed transactions as locally as possible. It applies transaction repair to distributed commit. It proposes fast-pass commit optimization, which omits two-phase commit overhead for one-shot transactions. And it is open-sourced. Thank you very much.